Let's look at some examples of spherically symmetric potential density pairs. Let's start with a homogeneous sphere. A homogeneous sphere has density constant inside the radius r and the density 0 outside of this radius. The mass distribution then is simple to integrate, which yields. Now let's consider then the potential. For the potential, we need to integrate the mass. If we are outside of the sphere, according to Newton's second theorem, it's a 1/r potential with a constant mass. But inside of the sphere, then, we need to integrate. The potential can be considered to be a contribution of different shells, each one a mass 4 pi rho r squared dr, the mass of a shell. Now, because of Newton's theorem, we can then separate the mass distribution into inside and outside the radius r. And inside it, we can consider the mass inside of that radius. Outside it, then we need to do the integral. Well, beyond the radius big R, there is no mass, so we can stop the integration there. And this is the potential that we get in the end. So we can plot these quantities, the mass and the potential, also the acceleration. And this is how they look like. So the mass here is going with r to the cube until you reach the radius of the sphere. Here in the x-axis is the radius, normalized by the radius of the sphere. The potential is parabolic inside the sphere, and then goes as 1/r outside it. And the acceleration then is the gradient of this potential. See, you have a linear acceleration inside, and then 1/r squared outside. We can use the same formalism to calculate the potential of dark halos. Dark matter does not interact with matter except gravitationally. As a result, any loss of energy is negligible, and the orbit of a dark matter particle does not settle into a disk like stars and gas. So the dark matter distribution around the galaxy should be spherically symmetric. Numerical simulations of the clustering of dark matter particles suggest that the density follows a profile of this type, as shown here, where A and rho naught are constants. Beta and alpha are also constants. Particularly popular is the model with alpha equal 1 and beta equal 3, which is called the NFW model, after Navarro, Frank, and White, an article from 1995. This formula contains only two free parameters. It's R naught and A. And the potential then becomes of this form. We can integrate this then to find the mass. The mass should be given by the integral of the density. So let's use sim pi to integrate this. So let's input the density and now integrate for the mass. So this is the mass distribution of the dark matter halo. Now we can calculate the gravitational potential, which is given by the integral of this mass distribution. Let's use sim pi again. So this is the mass, and this is the gravitational potential. Plotting this distribution. So this is the mass of an NFW dark matter halo. Now the mass in this model diverges logarithmically with the radius. But within a distance r, this is a good approximation for the mass of a dark matter halo.